Okay, chapter 2, section 4 is on the average rate of change of a function. Easy stuff. We're going to talk about the average rate of function, and we're going to look at the average rate of change for a linear function, and note that they have a constant rate of change. Just underline that. Okay, functions are often used to model changing quantities. In this section, we'll learn how to find the rate at which values of a function change as the input variables change. Okay, so we're all familiar with the concept of speed. If you drive a distance of 120 miles in 2 hours, then your average speed, or the rate of travel, is 120 divided by 2 to give you 60 miles per hour. Right, so we're used to seeing it in this sort of notation style, but that could be broken down, right? This could be broken down into 60 miles traveled in 1 hour. Right, when you see this little per hour thing, it really means this. So if we break it down into a fraction that has a 1 in the denominator, then we get to write it down or express it this way, 60 miles per hour. Anyway, so if you're traveling an average of 60 miles per hour, that means that every hour traveled, you drive 60 miles. Okay, so suppose you take a car trip and record the distance that you travel every few minutes. The distance s that you have traveled is a function of the time t. So, for example, just to give so we have time going on over here, and we have s of t happening over here. So let's say we're taking a trip to Las Vegas, right, a road trip, and this is measuring the distance traveled away from home, right? So home is here. You start off at home, and then you start driving, and you're keeping track of the distance traveled. Distance away from home. Away from home. In miles. Let's say home compared to Las Vegas. Let's say right here is Las Vegas, this distance away. So let's say that this is 450 miles away, just to throw a random number. So this is in miles. This looks like weird miles. Okay, so there's a distance of 450 miles between your home and Las Vegas. How are we going to get there? Okay, so we're going to do a car trip, a road trip. It could be, right, so time is going in this direction. So this is time in minutes. Well, we can use anything. Let's just use hours for now. I'm not sure if we want to change it, but any kind of measurement of time. It could be minutes, hours, days, weeks, doesn't matter. But in hours. So we want to be able to create some sort of a picture that would describe our distance away from home. So obviously at time 0, we start off at home, and then we head to Las Vegas. Road trip. Okay, so as we start off, we get in our car, we jump on the freeway. Maybe there's likely to be a lot of traffic in the beginning. It's LA, so maybe we don't get very far very quickly. In fact, if it's horizontal, like let's say this little segment here is horizontal, right? It means that we haven't moved anywhere. It's we're stopped somewhere. Maybe we stopped for gas or something. I don't know, but we're not moving anywhere. Now it moves horizontally this way because time keeps ticking away. So for this duration of time, you're the exact same distance away from home. Right, but then maybe you get back on the road and maybe traffic gets a little better, so you start going faster, right? The steeper this is, the faster you're traveling because you're getting away from home. So you're traveling pretty fast, and then maybe you run into a cop and you're like, oh, let's slow down, right? So you travel slower for a while, and then the cop gets off the freeway, like, okay, let's speed up. So now you go faster, and then maybe like, okay, let's stop for food. Maybe so for this duration of time, it's horizontal, right? If you decide, oh man, we forgot something at home, and you start heading back home, then it would start to come back down, indicating that you're getting closer to home. You're like, oh no, we didn't forget it, it's in the trunk. Oh, okay, so then you turn around and you start heading back toward Las Vegas. And then maybe as you start to get there, you get off the freeway and you're driving around the streets a little, so then maybe you're not traveling as fast away from home until you finally get there. So this could be one potential way of describing your road trip from home to Las Vegas. So what we're going to be looking at is the average rate of change, the average speed in this case, for the duration of the trip or for some portion thereof. So if I wanted to get the average rate of speed, I would look at the difference between this point and that point over there. So I would be looking at creating a line that connects these 2 points, and we want to find the change that occurs in that time frame. Or if I wanted to come up with the average speed between 2 other sets of points, like let's say these 2 sets of points right here, then I would find the change that occurred between these 2 points. So like let's say, just throwing some numbers out, let's say that this is at hour 2 and this is at hour 3. So let's say that this guy here at hour 2 would be s of 2. Well, yeah, okay. This is s of 2, and say that this is 210. So at exactly timestamp t equals to 2 hours, I'm 210 miles away from home. And at timestamp 3, this would be over here s of 3. And let's say at this point I'm exactly 390 miles away from home. Good. Okay, so if I want to find the average rate of change between these 2 points, I would want to connect them, and I want to find the slope of that line. I want to find the change that occurred here, which would be s of 3 minus s of 2, gives me the change that occurred in the vertical direction, which for these numbers that I made up, it would be the difference between 390 minus 210. So 180. And then in this direction, well, the difference is just 3 minus 2. Good. Okay. So the average rate of change would be 1 over 180 over 1. So average rate of change, average all over 3 minus 2. So for us, it would be equal to 180 divided by 1, or just 180. And keeping track of the units, this is 180 miles over 1 hour. 180 miles over 1 hour. So traveling at 180 miles per hour. Okay, so I don't know what kind of mode of transportation this is, but maybe not realistic for a car. Hopefully not realistic for a car. Good. Notice that when we say the average rate of change between these 2 timestamps, I know it's not realistic because of the numbers I made up, but whatever, we'll stick to it. Notice that we're saying that on average they traveled 180 miles per hour. That doesn't mean that they always traveled at that speed. Sometimes, as we saw for this part, they were stationary, right? They stopped for some food or something. Sometimes they were actually going in the other direction, so this would kind of register as a negative speed. I know it's kind of weird because in reality you would physically turn the car around and you'd be driving in the other direction. But for the purposes of this model, it just means you're going in reverse and you're going closer to home. So we have like a negative speed heading toward home. And then you turn around and you head back in the other direction and you speed up. So sometimes you're traveling faster than the average. Sometimes you're traveling negative, so definitely opposite to your average. And then sometimes slower than the average. But on the average during this, the time that elapsed here is the slope of that line, right? So the average rate of change is very, very similar to the slope of a line. A more realistic time, I think, well, I'd have to look to see. I'm not really sure how many miles Las Vegas is from here exactly, but anyway, so here is another similar idea, but just an easier graph. Right, so it's not quite as sort of detailed as the one I did, but it's still a graph that could represent a distance traveled on a trip. So here we again have the horizontal axis is t in hours, right? and we have various timestamps here. And then we have s in miles going in this direction. Right? So this is the s of t axis here, so it's in miles. And here it's in hours. Good. Okay, so after 1 hour, looks like they've gone about 50 miles. Good. So we would say, notation-wise, that this is s of 1 equals 50. So this is the ordered pair 1 comma s of 1, which is the same thing as 1 comma 50. Right, so those all mean the same thing, but I mean, it's getting kind of messy in here, but okay, that's fine. Let's, up here, this point would be 4. So t equals to 4, which means it would be the ordered pair 4 comma s of 4, where s of 4 is 200. So this would be equal to 4 comma 200. Okay, so we get a sense of all that. So the graph shows that we've traveled a total of 50 miles in 1 hour, 75 miles after 2 hours, 140 miles after 3 hours, and so on. Find the average speed between any 2 points on the trip. To find the speed of the average speed between any 2 points on the trip, we divide the distance traveled by the time elapsed. So, for instance, if we were looking at the average speed between hours 1 and 4, right? That's what this is describing here. Between hours 1 and 4. We want to be able to look at the slope of the line that connects these 2 points. So let me erase some of this because it's getting kind of heavy in here. We want to look at the line that connects these two. Oops, I don't want to use, how about blue? So we want to look at the line that connects these two right there. And we want to look at the change in the vertical direction divided by the change in the horizontal direction, just like slope. So the average rate of change will be equal to 150 divided by 3, which reduces down to 50. Right, so the distance traveled will be 150 miles in the time elapsed, which is 3 hours, which gets us to 50 miles per hour. Good. Notation-wise, again, we can replace it by s of 4 minus s of 1 all over 4 minus 1. And that's what this is. This guy is 1 comma s of 1. This guy is 1 comma s of 4. Good. This 150 is s of 4 minus s of 1. Right, where s of 4 was equal to 200, s of 1 was equal to 50. So the whole thing equals to 150. That's where this 150 comes from. And then here we have 4 minus 1. That's how we get 3. 4 minus 1. So that's why the average rate of speed between these 2 points is 150 divided by 3 to give you an average of 50. Right? So the slope of this line slope is going to be equal to 50 miles over 1 hour, so 50 miles per hour. This is the average rate of change. Right? It's all related. Any questions? No? 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 Okay, note that the average speed is different over different time intervals. So, for example, between 2 and 3 p.m., let's look at between 2 and 3 p.m., 2 o'clock we have 75, I think they said. It's kind of hard to tell from the graph here, right? So it looks about 75. Between 2 and 3, again, it's kind of hard to tell from here exactly. We lose a little bit of precision when we're reading just from the graph. But they did tell us here between, so 75 miles after 2 hours, 140 miles after 3 hours. So we know that s of 2 equals 75, and s of 3 equals 140. Good. So s of 2 equals 75, s of 3 equals 140. We divide them and we get 65 miles per hour. So the average speed between timestamp 2 p.m. and 3 p.m. during that hour, on average, the speed was 65 miles per hour. So a little bit different for different points. So in general, so here's more of a generic kind of graph. If we have this curvature, this red curve here, and we want to find, defined as a function f of x, and we want to find the average rate of change of the function f of x between the point x equals to a and x equals to b, then what we want to do is find the change in y and divide it by the change in x. And so from here, this point right here would be the point a comma f of a, and this point over here is the ordered pair b comma f of b. So the average rate of change is going to be the change in the the change in the y direction, right? This whole thing is delta y. Remember we said that little triangle reads as delta and it represents changing. So the change in the y. This guy over here is the change in the x, so delta x. The change in the x. So the change in the y divided by the change in the x, which is exactly what we define slope to be, right? So this is very closely related to that. It's in fact the slope of the line that connects these 2 points. Good. So the average rate of change is the slope of that. And notice that that becomes a pretty good approximation of the values of the red curvature. Right? It's not exactly equal to the values of the black line, but it's fairly close. It depends. And the closer that these 2 points get to each other along the red curve, the closer the approximation will be between the value of the secant black line that connects the 2 points and the value of the red one. Okay, so sometimes you'll just be given a graph and that's all you have to work with. And sometimes they'll give you the equation and that's all you have to work with, or sometimes they give you both, or maybe it's just easy to get one from the other. So let's say we have this equation now, f of x equals to x minus 3 squared. No real story associated with it, so it's not necessarily modeling anything in particular. But we have a function, so this one's f of x. This is the function f of x. And it's equal to x minus 3 squared. And we want to find the average rate of change between these 2 points, okay? X1 and x2, so that would be this one here. So really you're asking what is the slope of this little dotted blue line? That's what part A says. For part B, it's saying what's the average rate of change between 4 and 7, x equals to 4, x equals to 7. So it might be kind of hard to read some of these points. 1, 2, 3, 4. Maybe it looks like a 4. So that point right there, I'm going to say that it's equal to the point 1, comma 4. That's 0. Let's say that this one's a 4, comma 1. That this one's a 3, comma 0. And this one, I guess it's the 16. We'll go with the 16. 7, comma 16. So I was attempting to read it from the graph, but of course I have the equation for it. So let's just follow, for part A, let's just follow the instructions for the average rate of change. The average rate of change between these 2 points is going to be equal to f of 3 minus f of 1 divided by 3 minus 1. And now f of 3, that's equal to blank minus 3 squared minus blank minus 3 squared all over, and let's change colors here. So f of 3 is this equation evaluated at 3. And this equation is this one evaluated at 1. And the whole thing is over 3 and a 1. Put the subtraction here. Okay, so we just plug that in. We get 3 minus 3 is 0 squared, so that's just going to be 0. 0 minus, and then 1 minus 3 is negative 2. Squared becomes 4. 4 over 2. Which then just leads to negative 4 over 2. which leads to just -2. So the average rate of change between these 2 points is going to be -2. The slope of that dotted blue line is a -2. Okay, let's do the other one. 4 and 7. So for the other one, the average rates of change is going to be f of 7 minus f of 4 all over 7 minus 4. Okay, and again, it's blank minus 3 squared minus blank minus 3 squared. And then we subtract them down here. So let's plug in the green one again. So it's 7 goes in here, minus 3 squared, and 4 goes in here. That's f of 4 minus 3 squared. And then 7 and a 4 over here. Okay, that's going to be 4 squared is going to be 16, minus 1 squared is going to be 1, all over 3. So I get 15 over 3, which gives me a 5. Good. So we get an answer of 5. Really the biggest thing is to get used to this notation. Okay, so this is what the author wrote. For the first one, f of 3 minus f of 1, -4, and then the average rate of change would be f of 3 minus f of 1 all over 3 minus 1. So we get the same answer that the author wrote. So that's where we got this over here. And then for part B, f of 7 minus f of 1, same thing. We end up with a 15 in the numerator divided by 3, so we get a 5. Good. Linear functions have constant rates of change. So we know that a function of the form f of x equals to mx plus b is a linear function, and its graph is a line with a slope of m. On the other hand, if a function f has a constant rate of change, it turns out to be a linear function. So in general, the average rate of change of a linear function between any 2 points is the constant m. Right, so we're just pointing out if we happen to have a linear equation, it has a constant rate of change, and so the average rate of change between any 2 points is exactly equal to the constant, which is the slope of the line. Right, so they're all the same thing. It should be an easy questions here. So let f of x equal to 3x minus 5, the average rate of change of f between any 2 points. Okay, so note that if we are given that f of x equals to 3x minus 5, we can always go back to our standard way of describing this. Right? These two are equivalent to each other. And then this clearly fits the form of y equals mx plus b, which we are very familiar with. So clearly the m is being played by a 3. So m equals to 3. And the b is this guy. So 0, -5 is the y-intercept. Good. Okay, so now let's find the average rate of change by following our formula. And so by following our formula, we have that the average rate of change is equal to f of 1 minus f of 0 divided by 1 minus 0. This is for part A. And then f of 1, that's going to be equal to 3 minus, oops, not 3, 3 times blank minus 5 minus, and then 3 times blank minus 5, all of it all over 1 minus 0. Okay? And so f of 1 means we put a 1 in here. So it's going to be 3 times 1 minus 5 minus f of 0, which means we put a 0 in here, and then 1 minus 0. And then all we have to do is simplify this. So this is going to be 3 minus 5, that's going to be -2. -2 minus 0 minus 5, that's going to be -5 as well. Here, all over 1 minus 0 is just 1. So this becomes -2 plus 5 all over 1. So the whole thing is just going to be equal to 3. Okay, let's follow the same rules, just kind of getting used to the notation for finding the average rate of change. And it's good to practice with a simple equation because, you know, on your homework, you're just going to get a more complicated equation, but you follow the same steps. It's always this little formula for the average rate of change between two values. Okay, so let's try between, for part B, between x equals to 7, x equals to 3. For part B, average rate of change is going to be equal to f of 7 minus f of 4 all over this. Right, so it's a 7 and 3. So a 7 goes in here, a 3 goes in here, 7 goes in there, 3 goes in there. Okay, so this is going to be 3 times blank minus 5, and then we're going to insert the 7 in there, minus 3 times blank minus 5, minus, and then we're going to put a 7 in here, a 3 in here, a 7 in here, and a 3 in here. Okay, so that was the hard part. All we have to do is simplify now. 21 minus 5 is going to be equal to 16. 9 minus 5 is going to be 4. And then this becomes 4. So we'll end up with 16 minus 4 all over 4, which will give me 12 over 4, or 3. Good. All right, so C, last one. This time we're going to do it on average for these guys. And this one's a little bit trickier because they give you, let's look at this, they give you that x equals to a, x equals to a, and x equals to a plus h. This is probably the first time some of you have seen this style of notation. So let's look at it from this perspective. We just have some sort of graph here. Here's some sort of graph. We very often describe the x value. So we have x as some point a. This is x equals to a. And then if we let h be some distance, some positive value, then we can describe it as the distance to the right of some distance to the right of a. Well, I'm not red for this. Let's pick a different color. If we let h be some value like that, then we arrive at a new point over here, which is going to be the point a plus h. A plus h, right? Assuming that h is going to be some positive value strictly greater than 0, then we arrive at another point. So this is the point x equals to a plus h. So this style of notation allows us to leave this as a variable and this as another variable, but they're both connected by this h value, which is the distance, the gap between them. Good. So then the ordered pairs, this would be the point a, comma, f of a, whereas this point there would be the point a plus h is the input, comma, f of a plus h. Good. Questions, 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 questions? Okay, so we just follow our normal process through and find the average rate of change. So this is for part C. Average rate of change will be equal to f of blank minus f of blank, and then we subtract these. So it's going to be a plus h goes there, a goes there, a plus h goes here, and then a goes there. Right? Just following the same pattern that we did for the previous one. Right? We had x is equals to 7 goes there, x equals to 3 goes here, f of 7, f of 3. Right? The value to the right, so if we had here is 3, here is 7. So we start off with this right value, f of 7 minus f of 3, all over 7 minus 3. So that's why we start off with this right value, f of a plus h, minus f of a, all over this number minus this number. Okay, so now we're going to plug in those values. We had 3 times blank minus 5 minus 3 times blank minus 5 all over the difference of these two. So here we plug in an a plus h. Here we go with an a. Here we put an a plus h, and then we put an a. Good. So then we just simplify this. We're going to have to distribute this 3. Distribute, distribute. Combine like terms if possible. None are possible, then that's fine. And then we have to be careful to distribute this minus to both of these two terms. So this simplifies to be 3a plus 3h minus 5 minus 5 minus 3a plus 5 all over this, and then these two terms cancel. This one cancels with that one. Good. While we're at it, this one's going to cancel with this one, and this one's going to cancel with that one. So in the denominator, I'm left with just an h, and in the numerator, the only thing that survives is a 3h. It'll be 3h over h, and now the h's cancel, and we're left with just 3. Good. So no matter which average rate of change we wanted, we always got an answer of 3. And that's what we want to get away with here. So when we had this equation, 3x minus 5, we want to find the average rate of change when x changes from 0 to 1. We plugged it into our equation, we did our work, and we got an answer of the average rate of change equals to 3. When we wanted to find the average rate of change as x changes from 3 to 7 for this function, we plugged it all in, did our work, and we got an answer of 3. Right? And now if we leave it in general, let x equal some random real number value a, and let x equal to a plus h, where h is some positive number. Typically it's a positive number. It doesn't necessarily have to be the case, but the way we use it down the road in this notation, we'll end up defining it as a positive number. But for now it doesn't really matter. But x equals to some other value a plus h. We can visualize it this way. A and then a plus h. Of course, this is just some random function. It's not necessarily the function that we are working with. But then we plug it into our equation, work it all out, distribute, cancel, reduce, and we still end up with the same value of 3, which is all associated to this value in our equation, which is the slope. So of course, the average rate of change between any two random points on the line is going to be equal to 3, which is exactly equal to the slope of the line. Here's how the author did it. The average rate of change between x changes from 0 to 1, same thing we did, and get an answer of 3. Average rate of change as x changes from 3 to 7, same thing we did, on the meter. And then, slightly more messy, the average rate of change as x changes from a to a plus h. Similar. Okay, so the average rate of change is always 3 for a linear equation. Good. All right, that's it for average rate of change.